Imagine this every single second. Our planet gets a blast of energy from the sun that's equivalent to powering an insane 14,100 light bulbs all at once. Talk about one heck of a light show. Now, let's think about our daily routines. We flip switches on and off for various lights dozens of times each day without even batting an eye. It's second nature. But what if you forgot to turn off the lights before dozing off, only to wake up in a world that's seriously out of this world, literally all the way back in time? Sounds like something straight out of a sci-fi flick. You're probably wondering, what's light got to do with all this? Well, buckle up, because we've got some seriously mind-bending science on our hands. Last fall, two teams of super smart scientists from Oxford and Vienna took on a jaw-dropping experiment. They sent a tiny light particle, called a photon, hurtling back in time. Yes, you read that right. Using a fancy crystal, they managed to split the photon into two parts, creating what they dubbed quantum time reversal. Here's the crazy part. This single photon was now traveling both forward and backward through time at the same time. We're talking quantum physics on steroids, folks. Get ready for your mind to be blown. Now that we've dived into this wild time-traveling experiment with photons, let's set the record straight. We're not talking about Marty McFly-style human time travel just yet, but what if this research could crack the code to understanding how time travel might work? And here's the amazing part, all it takes is good old regular light. You know, that stuff pouring in through your window right now. But wait, there's more. Get ready to have your mind blown again. Did you know that sunbeams, yes, those super energizing rays we can't live without on Earth, aren't even the beginning of this incredible journey? Our universe itself lit up a whopping 14 billion years ago, long before our trusty sun came onto the scene. Buckle up, folks, because we're just scratching the surface of light's extraordinary powers. Let's go back to the very beginning, the Big Bang itself. Can you imagine a state so intense and hot it blocked even light from passing through? That was our universe just after its birth. It took an astonishing 400 million years for things to chill out and expand enough that particles could start interacting, forming hydrogen and giving us our first glimpse of light. But wait, the cosmic show wasn't over yet. As the universe continued to grow, it started to slow down from that rapid expansion phase, and something cool happened. The wavelength of that early light shifted towards the longer end of the spectrum. It transformed into microwaves, and these are still detectable today as a remnant glow known as cosmic background radiation or relic radiation. Now, here's where it gets truly mind-blowing. With just any ordinary telescope, you can tune into this ancient light right now. It's like witnessing the birth of our universe all over again. So, why doesn't this relic radiation fade away? The reason is simple. It's constantly filling the vast expanse of space. Think of it like a cosmic echo. We can still detect those ancient microwaves because they're present everywhere in our universe. Now, let's take a trip through history and explore how our understanding of light evolved. Long before Christ, ancient Greeks had some pretty interesting ideas about vision. They believed that our eyes shoot out beams to touch objects. Isn't it cool that we've come so far since then? Fast forward to 1672, when English physicist Isaac Newton shook things up with his groundbreaking new theory of light and colors. He revealed that light isn't just one pure, white entity as Aristotle thought, but rather a colorful mix of refracted rays. Newton definitely made some major breakthroughs, proving his theory with an awesome experiment where he shone a sunbeam through a prism and watched as 7 stunning rainbow colors appeared on his screen. But here's the thing, even though light is actually composed of all those different colors, we perceive it as white. So, why? It's because our eyes are pretty amazing, but they're also not super sensitive to sunlight. That's why we can't see the entire spectrum. You know how Newton thought light was made up of tiny particles called corpuscles, and they zoomed straight from the source. That theory explained how light bounces around and reflects off things, but it couldn't quite grasp how it bends when it passes through different materials. That's where refraction comes in. It wasn't until a talented Dutch physicist named Christian Huygens came along almost 2 decades later with his groundbreaking wave theory of light. Fast forward to the 19th century, and English physicist Thomas Young built upon Huygens' work, conducting an iconic experiment that showed us light indeed acts like a wave. Let's dive into Thomas Young's cool experiment. He shone light through 2 slits. Think of it like a mini obstacle course for light. If light really were made up of tiny particles, or corpuscles as Newton called them, we'd see two distinct lines on the screen behind the second slit, one from each slit. But nope, what Young actually saw was an interference pattern. This means that where the light waves from both slits met and overlapped, they either combined for a stronger beam in some areas or canceled each other out in others. It's all about wave power. So, let's talk about the sweet results. Behind Barrier 2, instead of seeing two clear lines, Young observed a series of alternating dark and light stripes that looked like a funky barcode. This was his interference pattern in action. For over 200 years, scientists thought they had it figured out. Light behaves like a wave. But then came Albert Einstein, the ultimate game changer, and showed us that light actually has both wave and particle properties. These tiny particles are called photons, and just like superheroes, they possess incredible powers. On one hand, they carry energy and have frequency, but on the other, they act like particles with impulse and direction. Light's duality is truly its superpower. So, let's dive into light's most epic abilities. With its dual nature, photons can travel enormous distances in no time as waves and still pack a punch as particles. They can literally knock electrons off course to power up solar panels or help plants photosynthesize. But there's so much more to this radiant superpower. Did you know that light is actually electromagnetic radiation that our eyes can detect? It all starts with the sun, where hydrogen atoms collide and ignite powerful energy explosions in its core. Hold up, isn't that some seriously intense stuff? Gamma radiation from the sun's core can be deadly because it packs an enormous punch, being millions of times brighter than what we see as light. But here's the cool part: these powerful photons can't escape the sun right away because they've got to travel through a thick layer of hydrogen atoms. And that journey takes a whopping 100 years. Yep, you read that right. It's a century before our photon even starts its trip out into space. As it makes its way through this radiant transfer zone, it loses some energy along the way. But that's not the end of its superpowers just yet. So what happens next? Well, these high-energy photons bounce around in the sun's outer layer, bumping into charged particles of superhot, ionized gas called plasma. It's like getting knocked around in a cosmic game of bumper cars. As they're pushed towards the surface, our photon has lost even more energy and is now classified as an X-ray. Now we're talking some serious waiting time on average. These photons chill out in this zone for about 170,000 years. That's a long nap. Some super persistent photons might hang around for millions of years before finally making their move. Eventually, they enter the convective zone, a whopping 200,000 kilometers wide, where things get really hot. As our photon collides with more plasma atoms, it gives them a serious heat boost. So much so that these atoms literally boil over, and then, guess what? They pass on the energy to send our photons straight to the surface in just about a week. But here's the cool part: as our photon journeys through these intense layers, it cools down enough to transform into visible light. You know, the kind we can actually see. It's like going from turbo boost mode to cruise control. After all that, it finally reaches the surface of the sun and is free at last, ready to embark on its epic space adventure. Now, the average photon gets to live out its days in the vast expanse of space, virtually immortal, with a lifespan stretching into billions of years. Talk about having plenty of time to travel. But there's a twist: photons heading towards Earth are on a tight schedule. They have a mere 8 minutes to make it here before their journey ends. It's like they're racing against the clock. Now, let's imagine what happens when our photon goes exploring. It might fly right into your house. But instead of just passing through the walls, this little light hero bounces around, bumping into every surface inside. Eventually, it loses all its energy and meets its match in one of the objects within, getting completely absorbed. This process is actually how everything heats up when we're near a warm source like the sun. Here's the cool science behind it. According to the first law of thermodynamics, energy can't be created or destroyed, it just changes forms. So, when you turn on that light in your room, an incredible number of trillions of photons flood the space. Most of them get sucked up by objects around you, but some are clever enough to bounce off surfaces as reflected light, and that's what makes everything visible. So, what makes all this possible? It's actually quite simple. When our surroundings are bathed in a steady stream of photons, like when the lamp is on, we can see everything around us. This constant flow of light energy is called photon flux. But here's the amazing part: all these processes, from the light source emitting its rays to their bounce and absorption, happen at lightning speed, roughly 1/millionth of a second. Now, you might be wondering if it's only artificial sources that radiate photons. Well, surprise, not quite. Some living organisms have an incredible ability called bioluminescence, which lets them glow in the dark. And did you know that scientists were curious to find out if humans could do this too? In 2009, a team of researchers in Japan decided to investigate just that. Could we unlock our own hidden superpower and start glowing like fireflies? So, what did these curious Japanese scientists discover? They published their findings in a journal called PLUSONE and set up an experiment that was out of this world, literally. They took volunteers into a super dark room, equipped them with some seriously cool cameras that can pick up even the faintest glow, and waited to see if any luminescence would shine through. And guess what? It did. The good news is that we all have a tiny bit of bioluminescent magic inside us. But here's the twist: it's not constant. Our glow actually changes throughout the day. You'll be thrilled less or maybe a little disappointed to know that people shone brightest in the afternoon, around 4 p.m., and dimmest at 10 a.m. The scientists linked this fluctuation to our body's metabolism, which means how we're burning energy to keep us going. Who knew being a human flashlight could be so fascinating? But here's the really cool part, and we mean that literally. Your body's glow is actually pretty chill. It doesn't generate any heat at all, unlike how you might feel when you're feeling super warm after exercise. It's more like a faint, gentle light show happening under the surface. Now, this might seem weird, but your face is apparently the brightest part of your glowing body. Who knew you had that hidden spotlight in there? Still, the scientists are stumped about which specific biochemical processes are causing all this radiant action. One thing's for sure though, if you could see it, your natural glow would be ridiculously faint. We're talking 1,000 times lower than what our eyes can normally pick up. Get this, our eyes can only pick up light waves that fall within an incredibly narrow range, between 4 and 800 terahertz. It's like trying to tune into a specific radio station. That's why we humans are totally clueless when it comes to infrared and ultraviolet rays, which are basically off the charts for us. But here's the thing: all this invisible light is actually super important for life on Earth, even if we can't see it. It's like light has yet another amazing power up its sleeve. So, now that you know about all these incredible abilities of light, let's get curious. Can we maybe harness some control over these powers? Do photons have a secret we could tap into? You're right, these powers are pretty out of this world. Since photons have zero mass, they can zoom through space at mind-boggling speeds. We're talking about the speed of light in a vacuum, which is roughly 300,000 kilometers per second. To put that into perspective, if you were to travel at just 1/10 of that speed, it would take you over 3 years to reach your next-door neighbor. So how do we possibly catch something that's moving so fast? Get ready to have your mind blown. Light can complete one full orbit around our planet in less than an instant. It's faster than 1/7 of a second. Now, you might have heard that nothing in this universe can top the speed of light, thanks to Albert Einstein's special relativity theory. But here's the most incredible part: time actually stands still for photons as they zip through space. If we could somehow tap into this amazing power and use it for space travel, things would get really cool. If a person could match the photon's insane speed, they'd experience time passing slower than everyone else on Earth. Can you imagine the adventures waiting to be had? Imagine being able to travel at mind-boggling speeds and witnessing our universe in ways no human ever has. As you approach stars at incredible velocities, they'd appear blue due to their light waves getting compressed. Meanwhile, the stars behind you would look red because their light waves are stretched out. This is known as an extreme Doppler effect, making distant galaxies seem like a colorful cosmic canvas. But hold on to your seat, things get really wild when you hit those crazy speeds. The hydrogen atoms around you would transform into a swarm of hazardous particles, leaving barely any time to enjoy the breathtaking views from the spacecraft window before it's back to navigating the dangers of space travel. Buckle up. As you zoom through space at near light speeds, hydrogen atoms start behaving like a cosmic assault, potentially causing your spacecraft to heat up in an instant. But don't worry, Scientists have thought this one through. Special shields could protect the ship from getting toasted. Now, about those Harvard researchers who stunned everyone by proposing an insane plan. They suggested harnessing the energy of a supernova explosion. Think of it like a cosmic shockwave to fuel your interstellar journey. And here's the best part. You wouldn't need any fuel. Instead, use a cleverly designed solar or magnetic sail to channel that blast into propulsion power. Mind blown yet? Get ready for the cool stuff. To make this interstellar ride happen, your spacecraft needs to rock a super lightweight sail. Think of it like a gigantic solar panel with material so thin and reflective that it only weighs half a gram per square meter, which is next to nothing. When we place this marvel about 1,000,000 kilometers away from the supernova explosion, it's time for the magic. The sail will unfurl and start harnessing that incredible energy, but here's the catch. Even with all this power, you'll only reach about 1/10 of light speed. But hold on, because scientists discovered another twist in the cosmic game. Photons themselves aren't always moving at top speed. When passing through certain materials or environments, they can actually slow down, like when light travels through a prism and gets bent. Talk about mind-bending science. Let's dive into more mind-blowing stuff. You know how we just talked about how some materials can slow down light? Well, scientists measure exactly how much a material slows down light by looking at something called the index of refraction. It's like a special number that tells us how much resistance an environment puts up against our speedy photons. On Earth, light moves almost as fast as it does in space, but only gets slightly held back. We're talking a teensy bit slower than usual, about 30 thousandths of a percent. But then, things get really cool. When light goes through something as dense as diamond, its speed drops by nearly half. Still, photons are crazy fast and can zoom through a diamond at over 100,000 kilometers per second. That's what I call lightning fast. So, the question remains, can light move faster than its top speed? You're right. According to our current understanding of physics, light can't move faster than its top speed, but that doesn't mean we can't get creative. The mind-bending thing about photons is that their whole existence is basically one fleeting moment. They don't experience time like we do. Think of it like trying to push an unmoving car. It's not going anywhere fast, and same with light once it hits max speed. But guess what? A team of genius researchers from the Lawrence Livermore National Laboratory in California and the University of Rochester in New York just shook things up. They conducted an experiment that actually made light move faster than its top speed. Yes, you read that right. Let's find out how they did it. These researchers are convinced that light has some super cool tricks up its sleeve, allowing it to play by its own rules. They set out to break free from the light speed limit, and boy, did they succeed. By pushing photons into a high-energy state of hot plasma, they caused these particles to collide and generate ripples or waves. Think of this as a chain reaction where individual photons are sending signals that move together as a group at their own pace. Then, using an ultra-powerful laser, the team knocked electrons loose from hydrogen and helium atoms, creating two distinct light sources with different pulse rates. By manipulating these pulses, they cleverly managed to control how fast the waves moved, taking them 30% beyond the speed of light. Light is truly the ultimate superhero, defying the rules of physics and pulling off mind-bending stunts. But here's the twist: can we actually boost its powers even further? Think about it like this. If scientists have already discovered some incredible abilities hidden within light, could they potentially unlock new ones to help us achieve amazing things for humanity's benefit? Let's dive into a groundbreaking experiment that proved just how far light's powers can be pushed. In 2016, Aussie researchers made headlines when they published their astonishing findings in Nature Physics, and what they did will leave you speechless. You heard that right, scientists managed to freeze light itself. Here's how they did it: by blasting infrared lasers into a super chilly atomic cloud. They essentially caught some of the light's energy, leaving the rest suspended and stuck. This groundbreaking research could soon make quantum computers as everyday as your smartphone. But what if we're not just talking about stopping light? Imagine being able to steer its movement like you're driving a sleek sports car. What would happen then? Get ready for a mind-blowing achievement. A team from Darmstadt University put on quite a show. They literally stopped a photon in its tracks and held it steady for 1 minute straight. Their incredible feat was published in Physical Review Letters, and here's how they did it. They used an opaque crystal as their playground. After chilling it to near freezing temperatures, they fired a laser to create a crazy quantum effect that made the crystal transparent for just one specific light frequency. Then, with precision timing, another laser hit the now translucent crystal, and guess what? They successfully stopped a photon in midair. Here's what happened next. Once they had stopped that photon cold, the scientists literally flipped a switch, or rather, turned off the transparency in their special crystal. And just like that, the laser light was trapped. They could even create a 3D light image with 3 distinct lines. Picture this: you shine a flashlight into a room and then slam the door shut, and when you reopen it later, the light spills out, free to roam again. The length of time the light stays captive. That depends on the type of crystal they're using. But here's the catch. For now, this whole mind-bending process only works in near-freezing temperatures, so it's still not ready for our everyday world just yet. We're one giant leap closer to building super-powerful quantum routers, which are essential for unleashing the ultimate security beast. A completely unhackable and lightning-fast quantum internet. But while we're on the path to that cutting-edge tech, scientists aren't stopping there. They're still exploring light's other tricks up their sleeves. A team from Utrecht University and Vienna University of Technology just dropped some major news in Nature Photonics. They successfully created one-of-a-kind light waves that can actually pass through solid objects. That's right, these game-changing photons are now capable of sneaking through materials we thought were impenetrable to light, opening doors to entirely new possibilities in fields like medicine and more. Let's dive deeper into this groundbreaking study. The researchers managed to craft special light beams that remain almost entirely intact while passing through solid, opaque surfaces. The result? These beams still produce a clear image on the other side, as if the obstacle was never there. To pull off this remarkable feat, they utilized zinc oxide and white powder, essentially making it look like a dark, uneven environment for their experiment. They then beamed in different specific signals of light through this mixture, observing how they'd appear on a sensor placed behind it. While we might not be seeing X-ray vision anytime soon, the possibilities here are truly exciting. Imagine being able to visualize what's inside complex materials, or even better detect hidden substances without causing damage. The future is indeed looking brighter. These mind-blowing findings are just the tip of the iceberg when it comes to their potential impact, especially in fields like medicine and biology. Right now, hospitals heavily rely on X-rays to peer inside our bodies since their longer wavelengths allow them to pass through skin. But what if we could harness visible light instead? The technology allowing us to focus light onto specific points within an object opens doors to entirely new possibilities. Just imagine being able to take a detailed look inside cells without any harm. And it doesn't stop there. Scientists are continuously pushing the boundaries, exploring alternative sources of light, and have already found ways to extract it from sound. The future is full of endless possibilities when you think about harnessing such raw power of nature in innovative ways. Let's dive deeper into this phenomenon known as sonoluminescence and uncover its secrets. It all begins with tiny bubbles formed within a liquid under high-pressure sound waves. These bubbles implode almost instantly when they reach their maximum size, releasing an enormous amount of heat and light in just a split second, causing the surrounding liquid to glow intensely for that fleeting moment. Now here's what gets really wild. Sonoluminescence can cause temperatures to skyrocket, reaching tens of thousands of degrees Celsius. To put this into perspective, that's even hotter than the surface of our sun. So while we've made some incredible progress in harnessing light from sound waves within liquids, there's still much left to explore and discover. Get ready for some mind-blowing history. Sonoluminescence was first stumbled upon all the way back in the 1930s, but it wasn't until the 80s that researchers really started digging into its secrets. As they dove deeper, they were thrilled to discover that this phenomenon isn't unique to water. Other liquids and even some gases can produce this spectacular light show. What's even more astonishing is just how much oomph these tiny bursts of light pack. Even a small amount of energy can result in a surprisingly powerful beam of light. So imagine this, the future where we ditch traditional bulbs and illuminate our homes with music alone. Sounds like sci-fi, right? Well, Thanks to the incredible work of scientists studying sonoluminescence, yesterday's dreams are becoming today's reality. All thanks to the awesome power of photons. You guys won't believe what's just made waves in the world of technology. A Canadian company called Hyper Stealth Biotechnology has pulled off something straight out of a superhero movie. They've created an ultra-cool material that makes things disappear before our very eyes, or rather, not appear at all. Dubbed quantum stealth, this thin and flexible plastic-like substance is packed with microscopic lenses that mess with light beams, scattering them in such a way that anything hiding behind it becomes completely invisible to the human eye. And that's not all. This material also works its magic on ultraviolet and infrared spectrums, making things invisible even to night vision gadgets and thermal cameras. So, if this tech were to become available, we could potentially turn invisible. But for now, let's just appreciate the awesome